Welcome. Glad you could make it. And I have a lot of slides. About a week ago I had 50, and I thought, well, I need to add some more. Now there's 101, so I'm going to skip some of them. But I'll put the slides up on SlideShare, so you'll be able to review what I talk about and then whatever I skip over. Some of it's basic stuff, so which leads me to another question. How many people have not used TensorFlow 1.x? Okay, so there are a few slides for you, and the rest is sort of assuming that you've been exposed to it, but consider yourselves lucky that you haven't. Things have changed a lot. So with that in mind, just a kind of an overview of some of the topics, the changes, how to upgrade, a few slides on that, and working with some of the new things in there. One of them is this at tf function, which is essentially it's a decorator. I call it annotation. That's kind of old school probably. And then generators. Has anybody worked with ECMA 6? It's the same generator stuff from 5 years ago. That when I saw it then, I was really confused. Now it's like, oh, okay, yeah, I get it. And datasets, not the data sets with data in them, but the datasets class. It's in tf.Data.Dataset, and it's kind of a wrapper around all sorts of data. And if you've worked with functional reactive programming, observables, that kind of stuff, RxJS, it's going to be a breeze for you. And then the main focus is actually tf.Keras for TensorFlow 2. That's where the TensorFlow team wants everybody to go right over there. So who's worked with Keras in any form? Okay, so there's standalone keras.io, which will live in perpetuity. There's Keras in 1.x, and then there's Keras in TensorFlow 2. It is very similar. It's essentially the same. And then a little bit of some other stuff just to show you. I got some code samples and a tiny bit about reinforcement learning. So lots of stuff to cover. We'll see how far we get. And so TensorFlow 2, as you know, is the new version, the new iteration of TensorFlow 1.x. It has all the good stuff that you would expect. It's open source. It's available on different platforms and hardware, CPUs, GPUs, TPUs, all that good stuff. And so what's the status? You can get some nightly builds right now because production isn't ready yet. Nobody seems to know for sure, or at least the people who know aren't saying anything. And it was supposed to be around Q2 spring, and we're in the spring. So I heard people say they think it'll be the end of the year. It's just speculation. So the latest one they have up there is actually April 17th, which I haven't seen any big difference between that and the alpha release. And so what about the platform I mentioned? Here's how you can, I think I'm going to turn sideways here. So some of the platforms that are supported, notice it's no GPU support, I guess, for that version, but there will be for other versions, later versions. That's how I interpret it. And how many people use Docker? Okay, so this slide's for you, and you can, when you go to that link, you'll get lots of detailed information about that. Okay. And what about 1.x? The latest right now, I think, is 1.14. I haven't checked in the last few weeks. The current stable one is 1.13.1. Now, after TensorFlow 2 is production, you get another year of support, and then that's it. So as soon as, now keep in mind that 1.x will be considered legacy code, but they'll continue supporting it, just some security-related features. So you got some breathing room. And I already kind of said pretty much, the TensorFlow 2. As far as installation, it's the same as before when you use pip, and there's how you install the alpha. And of course, that's going to change when they come out with the newer releases. Use cases, pretty much the same. This is the same slide even for TensorFlow 1.x. It's everything you can think of for the most part. It would almost be easier to say, what it doesn't support or cover use cases. And some of the changes, as you probably know, or if you don't, it's eager execution, which was actually brought out and made available in 1.4.1, believe it or not. A few toy examples, that was it, nothing else. And so a year later, they came out and actually make that the default. I think it was influenced by PyTorch. And so I mentioned the @tf function decorator. You would use that instead of the session code. And of course, don't clap too hard. tf.Session is gone. I'm really happy about that. And so there's also autograph that generates some code behind the scenes, some graph-related code when you decorate your Python functions. You don't have to decorate all the functions. Most of them don't really benefit from it. And there's some guidelines about that, when it'll be helpful. And but just be familiar with it. It'd be a good idea. So the generators is, again, the stuff I was telling you about. I'm going to show you some examples. And then the last two are related. I don't have code samples for that, but has to do with when you're in a particular layer, if you want to differentiate stuff or not. Again, I think that was influenced by PyTorch. So that's the stuff that's gone. And no global variables. Scopes are gone. I thought that was kind of convenient, but they thought otherwise. And so to do the upgrade, here's a couple of points. You need to, as of a few weeks ago, you have to do pip install, not pip3. With pip3, they don't have the upgrade script. So just keep that in mind, unless they've changed it. And when you do so, here's how to upgrade a particular file. One Python script, so that's the syntax, the in file, the out file, and it generates a report, what succeeded, what didn't, issues. And you can upgrade the entire directory. Now, don't make any changes to the signature of the methods, because it assumes that it's the 1.x format, style, ordering. So if you do, it's going to fail. And another assumption is that you have import TensorFlow as TF. That's another key assumption. So I tried with it a little bit, experimented, upgrading and so forth. I just use TensorFlow 2 now, except for my classes where we still do TensorFlow 1. And you can also upgrade your notebooks and so forth. So useful information. And if you want to find the versions of TensorFlow, there's a simple Python script. And that's what I have for TensorFlow Keras and NumPy. And so for those of you who aren't familiar with TensorFlow, essentially a tensor is a multidimensional array with other stuff. So it's enhanced to support lots of different kinds of operations. And the dimensionality, as you can see, essentially follows the dimensions of a matrix, if you will, or an object. So 0, 1, 2, 3, 4. Generally, you don't have to go past a fourth dimensional array or four-dimensional tensor. That's probably with video. And three-dimensional is with just static images. So the eager execution, one key point, you need Python 3. I think it's possible to backward port stuff. I didn't do that. So you could modify your code. And when you run that upgrade script, it doesn't change the order of anything. It puts something, it inserts, it modifies the namespace. So it puts, if there's method is ABC, it'll be something like compat.v1.abc, something like that. So you can play with that if you want to. Who's working with TensorFlow 1 and is not planning to upgrade to TensorFlow 2? Okay, so you don't need to worry about this. And as I mentioned, it's the default mode. And I keep looking there because I can't see my screen very well for some reason. So another small change you can see there, instead of matmul, now it's in linalg, which is, I guess, linear algebra. So they've kind of moved some things around, minor detail. And so you can see The first print statement gives you the metadata and also the value. And then the second one gives you just the pure value when you invoke .numpy. And now some of the operations, pretty much what you'd expect. Constant strings, tensors, arrays, so on and so forth. And so the primitives, in case for the people who haven't worked with TensorFlow, constants are initialized and immutable. So there are some languages that do that, but that's kind of explicit in TensorFlow 1 and 2. And the output from that code is just a little bit different, very tiny, tiny difference, I would say. But, it's good to know. So a little bit more. Notice that tf.variable, the V is a capital letter. Why do you think that is? Because it's a class. So it's not by accident. When you see capital letters, it's always going to be a class, whereas constant isn't. And some arithmetic stuff, pretty much what you would expect, same as 1.x. And so there's the output, which we would have expected. And a little bit about loops. We can have for loops and while loops. I'll just show you a very, very simple one. So what do you think this will print? 0 to 4 or 1 to 5? Well, 1 to 5, because they added 1. And then what do you think this will print? Is that going to be a terminating loop? What do you think? It's not an example of the halting problem. That's the actual output. So I'm not sure why you would want to do this exactly, but if you had to, you can do it fairly easily. So I guess one thing you may have noticed in the little bit of code I've done so far, TensorFlow 2 looks a lot like Python, and that's intentional. So how many people work with Python? Just about everybody. How many people work with R? How many people work with both? All right, okay, good. And I just read an article, something about, maybe it was clickbait. It was, is R losing the battle to Python? I had to read it. I wasn't convinced, but, so. Anyway, here's an example where we're converting a NumPy array to a tensor. Again, sometimes you need it, not that often. And so the index values, I skipped over that. Here we have at the bottom tf tensor 0 and 2, so that would be index 0 is the value 1.3, and then index at 2 is value 4. Pretty straightforward, simple stuff. Random numbers, one little detail. It's kind of minor, but it won't work if you don't do this. In 1.x, it's random underscore normal. So now they put a dot. So they moved it to a different namespace. And does anybody know what truncated normal does? It's sort of convenient. Well, if you need it, it's convenient. If not, then I guess. So what happens is you look at a normal distribution and you take two standard deviations on both sides of the mean, and all the values that are generated are in that interval. So if you generate a value that's outside of that, it'll generate it again. So it's kind of a truncated normal, well, hence the name. So that can be useful sometimes. And some other simple examples, the standard deviation, the mean, just very straightforward mechanical stuff. And some of the useful APIs, as you can probably imagine, tf0s fills it with zeros, tf1s is ones fill, you can specify the value. And then shape, rank, and range. What's the difference between them? What's the shape versus the rank?
Is shape like height and width, or the amount of lengths of each dimension? I don't know what rank would be.
The rank is the the numbers required to specify the number of elements in each dimension. So if it's 2 by 5 by 12, the rank is 3. So it's not the rank of a matrix. Is anyone familiar with that term? It's the number of linearly independent rows in a matrix, which is a different thing completely. And so here we have TF range. It's like a for loop. It's just, that's the syntax. It essentially does that. And that's the output of the range. And then, now, this is the part that I like. Who's familiar with either, they're called lazy operators, or they're also sometimes called intermediate operators? Anyone heard of those? Things like filter, map, batch, take, those sorts of things. So these are associated with the tf.Data.Dataset class. And they're very, very convenient because they're very expressive, and you can create some very compact and powerful code by using method chaining. So filter, for example, will take a lambda expression and then return some sort of result. So generally what a filter does is you give it a set of numbers and it returns a subset based on some Boolean condition. So if the condition is the number is divisible by 2, then it'll return the subset of numbers that are even, if there are any. Whereas a map is a set of numbers again, and then you specify a function, and then that function is applied to those numbers. So generally, a map will return a different set of numbers. So you could say something like, for each of the numbers, you might return 3 times the value. Or you could also have a smaller set of numbers that don't have to be in that set at all. You could take the numbers from, say, 10 to 20, and then return the result of the number modulo 2. So it's either going to be a 0 or 1, neither of which is in that set. So there's no real correlation between that. But generally, in many cases, when you're manipulating them, you're going to have some transformation of the original set of numbers. Flat map flattens things out. Batch says how many you want to take at a time. I have some examples of these. Take says take 5. It gives you just 5 of whatever's in the data set. And zip, you take 2 sets like this. You take them pairwise together, and that zips them. I don't know if that's an intuitive name, but that's kind of common to use that particular terminology. And then flat map is sort of related, but I won't go into that. So well, that's sort of what I said here. The technical definition of a map is that it's a projection, which really kind of tells you nothing if you don't know what that means. And then the flat map I've described, and also the filter as well. And so these are just essentially what I was saying. I'll show you the examples, it'll be clearer. So now, tf.Data.Dataset acts as a wrapper around data sources. They could be from NumPy arrays, they can be just about anything actually. You can get it from a CSV file. So it's a nice abstraction that using that, you don't have to deal with some of the idiosyncrasies of the data source. And so lazy operators, as I mentioned, those are the things I just described. And then they use generators versus iterators, and I'll show you what that means. Now, here we have, there's 2 different types of methods that you can use. There's a slight distinction. And the one where you go from tensors, you see the data source is a 1 by 2 by 2 array tensor. And so what it does is it returns everything as one item. Whereas if you use this one from tensor slices, it takes each element individually. So as you can see, the sec down below, it's a little bit different. So it took them up above, it's one element. So 1 by array or tensor, whereas here you have 2 separate elements, just so you know the difference there. And so how do we create a data set and manipulate it? Very simple. Here we have in NumPy a range where we get the numbers from 0 to 9. And that's how you create the data set. That's it. Pretty simple. Nothing fancy. It doesn't do anything, but that's how you create it. So now let's look at how to do it. I'm going to come back to the details for 2 in a minute. If you want to do it in 1.x, you do the same initialization for x, same with ds, and now here we have ds.map. Now what do you think that does? It's a lambda expression. It's like an anonymous function. And what will it do? It takes whatever input it's given, it will add 1 to it. That's it. Kind of contrived, but just to give you an example. Now, the iterator, there's 4 types in 1.x, and the one-shot iterator is a common one. There's also initializable. If you've worked with cursors, an iterator is like a cursor, and the initializable one is like a reusable cursor. You can move it around. A normal, standard, vanilla cursor, you can only go forward from beginning to end. That's kind of what this does. And so there's a loop for printing the values, and so there's a getNext method in the iterator. And then it just prints it. You don't have to print everything, but I just did for this particular example. Now, we're going back to TensorFlow 2. I changed this so that it's 0 to 5, or 0 through 4 inclusive. Now we have a slightly different method. We have the from_generator method. What does that mean? There's a Python function called gener. I just called it that for convenience. You can call it whatever you want. And what it says is that use this Python class to get the stuff, to get the numbers, in essence. And that thing, that tf.int64, tells you what it's going to return. And so if it returns 2 elements, you'd have to put into the same, it'd be tf.int64, comma, and then the same, and if it's a third, and so forth. And now, down below, we have 2 loops. What do you think they print? I'll show you the results and then explain why. The 2 loops, either what's going to happen is either the second one is going to be twice the first, or it's going to be an error, or it's going to be the same. So you got 1 chance out of 3. And it turns out it's the same. When there's nothing to print, it does nothing. So there's no error message. So that's kind of good, I guess. It doesn't throw an error. But if you want to be alerted to that fact, then you won't be. And so here's the part about the generators. To me, the semantics of generators is more like a pipe. So you have a writer and a reader. And the key word there is yield. Typically when you have a loop, it executes everything from beginning to end. And so you would expect that the values would be multiples of 3 from 0 to 12, just printed immediately. However, the yield acts as a kind of like the writer, in that it writes an element to the pipe and then it stops. The code here, since we're using gener as the generator, when you see down below, see the value in take ds.take, it's going to go up there and invoke that the generator. For the initial value of I is going to be 0, and it's going to return 3 times 0 and then stop. So just to be a little bit clearer on this, it's not quite like a pipe. Generally is you write to a pipe and you read. And if you read first, you have to wait until a pipe writes something there. This is pull oriented. The pipe doesn't write anything. It's the reader that requests something, and then the writer writes to it. Just a little fine distinction, in case you're wondering. Has anybody worked with Golang? Okay, well, it's like channels there. They have a similar concept. So that's it with generators. You generate 1 element at a time, just with your normal syntax, like we did before in the other example, same syntax. The only thing is that you need the from_generator method. You have to specify what the Python function is, and you got to specify the return type. And then you have to use the yield keyword. If you don't use yield, it's just going to print. So that's something to experiment so until you're, who likes this syntax? Okay, 3. How many think it's obvious? Well, when I first saw it with ECMA 6, I didn't think so. Now I think it is. I had 5 years to get used to it, so. And the next thing I want to show you, again, the difference in TensorFlow 1.x and TensorFlow 2 with map and take. Remember, take just specifies, you specify a number of things that you want. And in this particular case, since it's TensorFlow 1.x, we have enabled eager execution here. And notice the next one, we have tf.data text line data set. So it's going to read stuff from a text file, which happens to be this one. It's very simple, 5 lines of text. So what does this do? Well, it invokes the map operator. And in that, it has a lambda expression, which, given any line that is given, that is passed to it, which is going to be 1 line at a time from the data set, what does it do? It splits the line into its values. It just tokenizes it. And I don't have the TensorFlow 2 version because TensorFlow 2, I couldn't find where string split lives. So as soon as I find that, then I'll be able to do that example. And now what do we have at the bottom? We don't actually need the try except because it only takes 2 things, and there's 5 elements in the array, in the text file. So it's not going to throw any errors. But if you wanted to, if you needed to, you could do something like that. So what do we get? We get this. And you can see all the metadata that's there, and you see this is file line 1 and file line 2, so it does work. Now, how about the TensorFlow 2 version? Very, very similar. Oh, so I shouldn't say, not of the same example, but the TensorFlow 2 version of map and take. Here's an example where we have an array, NumPy array. We got 4 numbers. And look at our data set from tensor slices. It's going to take each number individually. And now what does it do? There's a ds.map. Then there's a lambda expression. What does that do? Doubles the numbers. So it's going to be 2, 4, 6, 8. Then another map adds 1, so it's 3, 5, 7, 9. Then it cubes them. So then at the bottom we take 4, which happens to be the number of elements there. You could take fewer if you wanted to. And here's the output. So those are the cubes of 3, 5, 7, and 9, if you needed to do that. The key takeaway point, though, is the fact that you can do this method chaining with all of these things. It doesn't have to be all map. It could be any combination of whatever it is that you need. And it's very powerful. And you could do this, you could have pages of code. I wouldn't advise that because debugging it could become a nightmare. So what I would recommend is maybe 3 or 4 together, test them, and then when it's working, then start combining. But probably, have some documentation for the poor soul who has to inherit your code and enhance it and has no idea what it means. So that would be nice. Or maybe for you, 6 months later when you come back. That happens to me all the time. And so a little bit more. Now this is a little bit less intuitive. What do you think this does? I'll let you try it at home. I just want to point out that we have, once again, tf.Data.Dataset from generator, same name for the Python function. And notice we have tf.int64, we have 3 of them. So it's not going to return 1 number, it's going to return 3 numbers as an entity. And there's a while loop in there, and notice we have I plus 1, I plus 2. So you can kind of sort of guess what it's doing. And of course it needs the yield operator. And then since it's a while loop and not a for loop, I had to manually increment I by 3. So it's not a big deal, but I mean, I'm not saying this is the best way to do this code, but if you had to, you could do something like this and then the for loop at the bottom. Another one where maybe it's not so intuitive. This is with the 2 data sets, and this one, because the first one is the normal range, but then we've got a range of a different set of negative numbers, and then we have the zip and batch 4 and then take 10. So I'll let you practice on that. So now we come to the main part of TensorFlow 2, which according to people at Google, some have said, TensorFlow 2 is keras. Up until now, we didn't see anything about keras, but that's what they say. That's where they want everyone to go. The keras in TensorFlow 2 lives in tf.Keras. And it looks the same as the other stuff, it's just that the namespace is a little bit different. They've reorganized things, and it's done in a way that's sensible. The models, well, there's a sequential model. That's one of them. It's in there. Optimizers, Atom, RMS prop, all that stuff, they're in there. Utils, there's 1, 2 categorical, there's 1 utility function in there. There's some others, but that's the only one I recognize. And regularizers, more stuff. For, what is it, L1, L2, lasso and ridge regression, ridge optimization. So here's an example of the model, the sequential model. And these are some of the things that you can do. And for the most part, you'll probably be loading it and saving it, but you can also get it from JSON or from YAML if you want to. I haven't had occasion to do that yet, but it's good to know. And from a config file as well. So that's convenient. So now here are the layers. You recognize these things? The activation functions, they're all there. That I like. And so conv2d for CNNs is there. And look at RNN, LSTM. It's all nicely batch numbers. And bidirectional. Has anyone worked with bidirectional LSTMs? Those are very, very common now in NLP-related systems like BERT, Elmo, and those other ones. And we'll get to that a little bit later. But essentially, that's kind of the standard almost, that for any kind of new results in NLP with deep learning, they're going to be using those. So it's a nice, and there's some other ones as well, but these are the most common ones. And activation functions, you get the ReLU group in there, sigmoid, softmax, tanh. There's also hardmax. I don't remember if that's in there or not. And the data sets, no, this is the data sets with data, not the tf.Data.Dataset. And so you can see it's different because it's tf.Keras.Dataset. So all of the standard ones, pretty much, except for which one's missing? The flowers, yes, iris, that's right. But you can get that in sklearn. They have that built in, so you're okay. This one I don't use. Some of it was in the contrib, which is gone. They kind of moved it over. They've rearranged the furniture, dropped a lot of stuff, kept some of it. The peephole LSTM cell, I don't know if you've heard of that. It's one of those, I've never seen any code actually using it, but it is an LSTM so that the different gates can have access to the long-term cell state. Not sure why you would need to do that, but if you had to, there you have it. And we'll get to an example of that, of the cell state and the gates. They're the optimizers, some of them. And callbacks, when would you use those? The only two that, for me, well, there's actually more than, they're all useful. The early stopping is a class that you invoke when you're in the training process, and 2 consecutive iterations have reduced the loss function by a value less than an amount that you specify. So if the loss decreases by less than 10 to the negative 4, you're probably done, maybe. And so there's no point in continuing the loop. You might be halfway through or a quarter of the way through, and why bother calculating? You can still do it, of course, but if you wanted to make sure you don't go beyond that, then you could have used that class. Now, that doesn't mean that if you continue the iterations, that difference might increase greater than that threshold value. That's possible too. But that's your decision that you can make, and it's convenient. And also it's in TensorBoard, so you can launch, this code can run straight, can run in Google Collaboratory. And so some of the losses, I think you're probably familiar with some of them. By cross entropy, of course. There's about 10 of them in TensorFlow. So I'm not sure where the other ones are. I didn't go look for them. The mean squared error, mean absolute error. There's also a couple there. Who's familiar with KL divergence, Kullback-Leibler divergence, based on cross entropy and so on? There it is. What I'm not sure of is how the second one differs from KLD. So I have to take a look at that. They look like, I'm sure there's a difference there. And then the categorical cross entropy, of course, when you have categorical data. Binary cross entropy, kind of interchangeable sort of with sigmoid, but I've heard it's supposed to be the same, but I think I read something on Stack Overflow that it didn't quite work always as expected, so you need to test it if you're going to use either one of those. And the regularizers, as I mentioned, the utils, the pre-processing one, again, is obviously for text. So here's sort of the summary of what's happened to the main stuff in TensorFlow 1. So core has been reduced. The layers I mentioned, is now it's tf.keras.layers. And the estimator stuff, and then the contrib estimator. Now, estimators are supposed to be a layer of abstraction over tf.keras.layers. And I don't know if it's just me, but I have yet to see an example with estimators that's easier, more intuitive than just using the straight layers. And I asked somebody over at Google, and please give me that code that shows that. And the response was that estimators were a solution to a problem that no longer exists. So I don't know what that means, but I'm kind of glad. I don't have to worry. I got other things to worry about, not these estimators. Okay, so that's kind of the quick, super fast overview of the first part. Now I want to just, not to get into the details of it, but I just want to, there's one concept that I want to talk about. And as you probably remember, if you've seen this before, you generally, when you're training a model, a neural network, you have an input layer, which is a vector of numbers, that is then multiplied by the matrix that represents the weights between two adjacent layers. And you take the vector times that matrix, then you add a bias vector, and then you pass that through an activation function. What happens, and that's the standard sort of pattern. That's very important. Just want to make a mental note of that because it's going to come up later. So it's generally vector times matrix plus a bias, and then apply this activation function. Sometimes you won't see the bias vector. That's because it can be added as the rightmost column of that matrix. They're identical in terms of functionality. They look different, but it's actually the same. So when you see one and you prefer the other, just sort of mentally translate back and forth between the two. And that's the pattern that I just want you to keep in mind, because it's going to come up a bit later. So this is how you would write the code in Keras. Notice that we have the sequential model, and then we're just adding a bunch of stuff. So what I showed you before was an artificial neural network, and MLP, multi-layer perceptron, is when it's fully connected. So that's sort of a subset of ANNs you could think of. And that's why the dents are there. They do the full, all complete connected stuff. And that's sort of, kind of almost it, the core of the model. And it just adds a bunch of layers, and then there's a compile step. And the training the method is called fit. So compile, fit, evaluate, predict, and so on and so forth. So pretty straightforward. Here's another example, pretty much the same thing, the difference being that now, instead of doing .add, you just specify an array of layers. And you see they're separated by commas, so you just this and this, that's it. So you just do something like that. There are trade-offs, depending on which method that you prefer. The functionality is the same. There's another functional approach, which I don't have an example of that. And there's also where you specify a custom Python class, which subclass is model, and you have to initialize. There's the init method and the call method, which you can do that too. If you really like Python, you'll probably like that. I just go with whatever is the simplest, easiest, straightforward to understand for me and everybody else. So now, who's worked with CNNs? Okay, so these are for lots of things. Image classification, and I'll just briefly describe them. What happens is you have an image, and you, in the framework that you're using, TensorFlow, Keras, whatever, you specify these little things called like a 3x3 matrix, 5x5, even 1x1 of values. The numbers are taken care of for you by the system. And they're called convolutions, or they're called kernels. Or sorry, filters are kernels. And so what you do is the system will take the little matrix and scan it across, and as it does so, it computes the inner product of that 3x3 matrix with the underlying pixel values, if it's an image, and ends up constructing something called a feature map. And the next step is to apply ReLU so that negative values are replaced by 0. The next thing is this max pooling, not intuitive. You divide the feature map into 2x2 rectangles, take the largest value, and you get a small array where you've thrown away 75% of the values. And as an alternative to that, there's also something called capsule networks, which retains more information and harder to train. Not important for us tonight. So going through this process, toward the end, what happens is all these little feature maps get concatenated, and the last layer you use the softmax function. That's the activation function that will take those numbers, produce a set of numbers between 0 and 1, whose sum equals 1. So it's a probability distribution. And over on the right, there are going to be 4 numbers. And you look at which position has the largest value, the largest percentage. Let's say it's the first one. So that's index 0. That image over there has a label. It's going to be one of those 3, 4 that are shown over there. So you one-hot encode that. So it's going to be something like 1, 0, 0, 0, 0, 1, 0, 0. It's like an identity matrix. So if we're just pretending that it's the largest value is in the bird position. So that has index 1 has the largest percentage. We look at the index position of where the 1 occurs in the one-hot encoding. If those index positions are the same, it's a match. So you do this with every image. Add up the ones that are matches, divide by the total number of images that you've processed during training, multiply by 100, there's your percentage. And you kind of do that with the testing part, except it's only forward propagation. You don't do back propagation. Compute the percentage similar, and then you compare. And then, the overfitting, blah, blah, blah. All that kind of stuff. So anyway, here's how you define this in Keras. See, that's it. Basically, that's it. Conv2D and max pooling. And the conv2D specifies ReLU, the second step. And you can have multiple. I mean, this is a very, very small example. But in essence, whatever you need to do, you'll get from tf.Keras layers, whatever methods you need, classes you need to invoke. And so what about RNNs? Does anyone work with those? Recurrent neural networks. So the thing is about CNNs or ANNs, MLPs, they're essentially stateless. So when you go from left to right, whatever's happened, the current layer, you go to the next layer, the rest, nothing is retained in terms of kept track of. And that's perfectly okay. But if you want to do some, keep track of what's happened before, a certain amount of history, you have to use something else. And it turns out that it's these RNNs. is one type of architecture. And so there's the basic simple RNN, the LSTMs, GRUs, and there's a few other ones as well. And so the LSTMs they're a lot more complicated. We'll get to that in a minute. They overcome some of the deficiencies of RNNs. So as I mentioned, some of the things that you can do, you can actually use RNNs with MNIST data. It's kind of interesting. The technique there is clever yet non-intuitive, I guess I could put it. Time series data. Also, I found an example online with an RNN and Trump's tweets, which, regardless of your affiliation, it seems to interest people a lot. So when I do that in class, it kind of gets people, everybody wants to try that one out. And so just kind of graphically, with the typical feed-forward situation, we have the input at the bottom, the hidden, and then the output. It's just one directional. Whereas the RNN, it's a feedback loop, basically. If you've worked with circuits, this is very simple. You'll be used to doing this kind of thing. And so this formula, you remember I was saying before, the vector times a matrix plus a bias, and then apply an activation function. It's similar to that. The difference is that, see, we have it's time series stuff. So at time t, we have input xt, and the previous output is h of t minus 1. And remember, we feed that back in. And so the comma means concatenate. So we concatenate that and just get a longer vector. And where's the bias? Well, it's in the matrix W, which the syntax is a little confusing. But what it really means is some function with parameter. I mean, that's the weight matrix W. So you W times the concatenation plus the bias, and then apply an activation. It's basically the same as what we did before, remember? About 3 minutes ago? Same pattern, more or less. And so here's might be a little bit easier to see. We have inputs at time t1, time 1, 2, and 3. And as you can see, the outputs, so H0 combines with X1 multiplied by W, and then it's H1 and X2 multiplied by W. It's the same matrix W. So that's the structure of an RNN, a basic RNN. And these are some of the parameters that are used. This is typically what are specified. You don't have to memorize this, but if it's the number of steps, this is the time steps. I put comments on the right. And then the number of neurons and outputs and so on and so forth. So the thing about it is that with RNNs is that there's backpropagation. And it's called BPTT, backpropagation through time. So we're looking at the ANN, and actually the same thing with CNNs. You go forward propagation, then you go back. You have a cost function and an optimizer and a learning rate, and you have to go back to update the weights and stuff. In the case of CNNs, you update the values in those filters. Except that with RNNs, you got to go back through all those extra layers. It's a lot more complicated. It still works usually, but not always. That's one thing. So there's truncated backpropagation through time. That's kind of a workaround. And so there's the vanishing exploding gradient. Who's heard of those terms? Okay, so for those of you who haven't, when you go from right to left, backward error propagation or backprop, you're calculating values to update the weights between neurons in adjacent layers. And it's a product of a bunch of numbers. Well, if those numbers are really small, the product goes very quickly to 0. So by the time you get back to the beginning of the input layer, there's almost negligible updates. And so when that happens, that's the vanishing gradient. Exploding is the opposite. It's easier to deal with. You just put some conditional, say if it's bigger than some number, chop it off. Well, anyway, RNNs have issues with this. And also they don't, there's a limit to what they can do. It's almost like a queue. You fill up a queue and then you start adding more stuff and things fall off the end, kind of. It's just not the best solution. So this is where LSTMs come into the picture. And one of the persons, only 20 years ago, not that long ago, one of the persons, the inventors, co-inventors, was here at a meetup, actually, I think, about 4 or 5 months ago. I didn't have a chance to attend. And so it's got some improvements, some of them avoiding the vanishing gradient. It's also contract things for long periods of time. It's really good with NLP-related stuff because you have things in a document that could be referred on page 1 and then maybe showing up later in that page or on the next page, and they're connected. You know, and sometimes you have to, I found myself reading stuff, I have to flip back to they can do that kind of stuff. It's kind of amazing, actually. And so, again, the usual stuff, pretty much, as we had before. And so, some of the advantages I kind of already alluded to. And the last one is a good point. You don't need to have equal increments in time when you're processing content. So you could work with stock data, for example, or things are not, it's not on a regular basis. Had a class, one student did a term project on predicting Bitcoin. It was very interesting. It was machine learning, so they didn't have access to deep learning stuff. So they went through a lot of extra pain. They could have just done that. It would have been a lot easier, but I didn't have the heart to tell them that. So they take my class and you'll find out. And so the thing about there's 3 gates. There's a forget gate, input gate, output gate, and then there's this central long-term memory part. So there's the long-term memory, and then at each time period, you've got this temporary input, the short-term. So that's why the combination of the two, long, short-term memory, is not an oxymoron. It really does make sense. And so you do different things with them, and I'm going to show you the diagram in a moment. Just a little bit more detail about the gates and the cell state, and of course they retain more content, more memory than basic RNNs. But they're actually a subclass of RNN. So the RNN class is the base class. And so here are some of the terms that you'll see. This is very similar to what we saw before. And you'll have this in code samples if you go, this is typically what you'll see. The values will be different, but you'll see num units is the number of units, the hidden layers, if you will, for these LSTMs or RNNs or GRUs. And I don't know if whenever I think about this stuff, it reminds me of, remember those old, what was it, the organ grinders? What were the dancing monkey, and the guy had that thing in his hands and he would expand it, he would play. It's an accordion? Not the full-size one. It's still an accordion. Yeah, so when you look at his clothes, you can't tell what's in there, and he pulls it out. It's like all these layers in there. That's what I think of when, for some reason, I don't know why, when I look at LSTMs. So here's kind of what's happening. See the num_units? That's the number of hidden layers. And it's doing that pattern that I told you about with this ANNs and with the MLPs and the RNN vector times matrix plus bias, pass-through and activation function. And of course with an RNN, it's not just the xt at time t, it's the previous output, ht minus 1, you get a longer vector, but similar pattern. And so what happens is all this processing takes place, and they got these outputs coming out at every stage in there, and it's the last one, the rightmost hidden layer inside the LSTM that emits an output, which is a one-dimensional vector. That's the thing that gets passed to the next LSTM. All that number crunching just to get that one vector. So brace yourselves. I know this looks like a hot mess, but it's not that bad when you think about it. like this. If you look at the bottom there, we have, you notice we have x of t and then h of t minus 1. That's the output from the previous time step. Look at the forget gate. Do you see the pattern? It's h of t minus 1, the previous output, at time t minus 1, concatenated with x of t, the current input. Then we multiply by a matrix, then add a bias, and then apply the sigmoid function. Just like what we did with the R and N. This is for the forget gate, and that's why there's the subscripts F. And then the input gate, there's the same thing except it's WI instead of WF, and B sub I instead of B sub F. But it's the same pattern. And then down below, the output gate, same pattern. And then there's a couple more in between, maybe not so obvious, but see that C tilde T? This is the intermediate new state. And it's inside of there, same pattern, except this time it's the tan H activation function instead of sigmoid. A little different. Now we get to the sort of tricky part, which is the totally non-intuitive part, which I would never have thought of. We calculate the new internal state by taking what's called the Hadamard product. It's basically an AND. And we multiply the forget gate with the previous internal state added to the product of the input gate and the intermediate internal state from the line above. And we're almost done. We already talked about the output. Now, that hidden state, that short-term thing, is the product of the output gate above, the result of that, and tan H of the internal state. And that's it. This I spend about, with LSTMs and so forth in the class, I spend about 6 hours. So you got the 5-minute version of that, so don't feel bad if it's confusing. This gave me a migraine the first time I saw it. It took me a long time to understand it. And then it was like, oh, it's not that bad. You'll feel that way too someday. Okay, so now, there we have it. If you want to do that, you don't have to understand any of that. Just use the Keras class, tf.Keras layers, LSTM cell. You're done. It does all that stuff for you. Now there's a slight difference, and I won't go into detail now. It's not that important. If you want to find out the difference between the LSTM class and LSTM cell, there's a link. And you can define a custom LSTM cell if you really want to. I've not done that yet. I'm not ready to go on that journey. And so the example I mentioned about bidirectional LSTMs, there it is. You just add that. There's actually one more detail which I didn't include. Unless they're aliased, which they aren't in this example, but it would be tf.Keras.layers.bidirectional. And funny enough, I like spelling it all out, even though you can use aliases, because I know exactly where everything is coming from. I feel more sure of what I'm doing, which isn't always the case. So. And now, something a little different. Has anyone heard of autoencoders? They're really kind of interesting, actually. Have you heard of PCA, Principal Component Analysis and Machine Learning, which is a technique kind of like SVD, singular value decomposition, in the same family, where you have a set of attributes, features, say 100 of them, and you want the top 3. So it gets rid of all the stuff that's sort of irrelevant. This is the deep learning counterpart, if you will, to PCA. You have an input layer and the output layer are the same. Then you have a layer in between, which kind of squashes it down to figure out what's the key stuff that's really happening. And that's the layer you're interested in, is actually that intermediate layer. And the interesting thing is there's all sorts of variations on this. If you go to Wikimedia, you'll find like 100 different images, and they're really interesting what people are doing. I'm not sure what their use cases are. I hope they have them, otherwise they're just pretty pictures. But one example, here's another one. a variational autoencoder. This one gets kind of a little bit more difficult, because what happens is that now, notice we have the hidden layer in between. You have the layer on the left and then the green layer. There's another pair, and there's the left of the middle layer is the encoder, and then the one on the other side is the decoder. And there are two probability distributions involved. And there's a loss function, and it uses gradient descent, and it involves Callback-Leibler divergence. And it gets pretty hairy when you're getting into the details of that. And so then when you're done, then it goes into a deep neural network. Now, why would anybody do something like this? Why go to all that trouble? Autonomous vehicles and ride-sharing type companies, they do stuff like this. You have a video coming in a live feed, so each image, a video is a bunch of images. So you pass that into CNN to process, then it goes into an LSTM, and then it goes to a variational autoencoder. So why would you use an LSTM with a CNN? Because you want to track things, so that you don't hit something or something doesn't hit you. So you got to anticipate, predict. You've got a trajectory and you predict, how to stay away from each other, kind of thing. So you need those two for sure. This isn't obvious that you would need that, but it's quite common. The big companies do this. And so there's more. You can actually do things like, well, this top article goes into a lot of detail about what I just showed you. And it even has a GitHub repository, and there's a glossary of terms. It's very lengthy. It'll take some time, but it's probably worth it. You can, and TensorFlow 2 with autoencoders, there's an example. I forgot to put in the link with TensorFlow 2 variational autoencoders, but you can find it. There's also a convolutional variational autoencoder. I never would have thought of that. I never would have thought of most of this stuff, actually. And so then the variational autoencoders and GANs, believe it or not. People are getting really amazingly creative. There's almost like a cult thing going on with GANs. I'm not cult in the negative sense, but they're very creative, very passionate, and they just do amazing things with that. So just a little bit more. Reinforcement learning, that's the hot thing. Actually, deep reinforcement learning. And in different fields, it's known by different names. Those of you who are background in mathematics, there's operations research. For those of you from psychology, remember classical operant conditioning? I remember the name, that's about it. And so they all kind of intersect. They're known by different things in different fields. And here's the diagram, which you will see. And so you have this agent, could be a program, person, whatever. It performs an action, goes to this thing called an environment, which then returns a new state, because you're in a state already, a new state and a reward, which, if you look at it, this tells you practically nothing. But you'll always see this diagram when you see reinforcement learning. And so the idea is it solves problems that involve deferred rewards, especially when the final reward is greater than the intermediate rewards. So if you try to use a greedy algorithm, it will fail, because they always say take the maximum at every step, and then at the end you'll have, doesn't work that way always. And I'll show you in a moment an example. Well, actually right now, here's a sort of a nice basic problem. You have 5 states, and you have transitions, or actions, transitions. So this action A has a reward 0, and that's the one that goes forward all the way across. So you get nothing. The other action, action 1, has a reward of 2. Well, that brings you back to the beginning every time. So if you use a greedy algorithm, what's going to happen? You're never going to get out of that first state. So the idea is for where reinforcement learning excels, and there's actually an algorithm, it's called the epsilon greedy algorithm. You use a greedy algorithm most of the time And some of the time you make a random choice. So it's kind of like a hybrid. It's also called simulated annealing or hill climbing with random restart. Similar concept. So just to make it simple, let's suppose that it's based on flipping a coin. If it's heads, we go forward. If it's tails, we go back. That's our random choice. So what would it take to go from state 0 to the last state? We have to flip what? 4 heads in a row. And what's the probability? If it's a well-balanced coin and all that, it's 1 out of 16. Very reasonable. What happens is with this epsilon greedy algorithm is that there's a loop and you go through different stuff, but ultimately the sort of the settled point, if you will, is you use the greedy algorithm 90% of the time and random choice 10%. So that would be flipping a coin where you get sort of a coin or something, a random number. So 1 chance out of 10 to go forward. So what do we need to do to get all the way to the end? Well, it's 1 over 10 to the 4th. So 1 chance in 10,000. Obviously a lot smaller, but it will get there. So that's kind of the idea behind reinforcement learning. That's why there's lots of trial and error. Most of it's error. But eventually when it works really, really well. And that was used in the AlphaGo. So just ask Lee Sedol about that. Wonder if he has nightmares. Just joking. So here's a slightly different one where now we have not just reinforcement learning, but deep reinforcement learning. And what happens is the reward step, it goes now, this agent is now a neural network. So deep reinforcement learning is the future, in my opinion. Robotics, games, NLP. Which one has the least barrier to entry? NLP. Chatbots. People are working on it as we speak. Startups. So if you want to get into something, there's been a tremendous amount of research going on, not recently, as in a year and a half. 2 years ago, Andrew Ng, you know, AI is the new electricity, he essentially said that reinforcement learning was kind of a waste of time. So it's gone from 0 to hero in about less than 2 years. And it's got tremendous potential. And so just to give you a little bit more, it's actually, believe it or not, TensorFlow calls it dopamine. I guess it's a good name. And it's for research, right? This is reinforcement learning. TF agents was announced during the, what do you call it, TensorFlow Summit or in March. And then there's also Keras reinforcement. There's a bunch of stuff actually out there. And the thing is that what I showed you is probably the simplest thing. There's a few other things that are part of the low-hanging fruit. But when you get into reinforcement learning, it looks like this eclectic mix of non-intuitive algorithms, and there's lots of them. And I'm trying to figure out a way to make it intuitively understandable, and I'm still working on it because they're not intuitive. But those algorithms people have spent a considerable amount of research on, and they do work in the right situations. So it's a long, steep learning curve, pretty much. And so just 2 more slides. I just came out with the Python for TensorFlow book. It's specifically focusing on the Python stuff for TensorFlow, hence the title. The second one is my publisher asked me because he thinks that TensorFlow 1 is going to be around for a long time. So, okay, he's going to make money off that. Okay, fine. The TensorFlow 2 book is coming out in a couple of months and has a lot of, all the stuff that I've talked about tonight is in the book. And the one last slide, these are classes that I have over at UCSC, over here, Santa Clara. And so the Python is a prerequisite for machine learning. Machine learning is a prerequisite for deep learning. And deep learning is a prerequisite for the one there, the advanced topics. We're going to get into the deep reinforcement learning, autonomous vehicles, GANs, AlphaGo 0. It's going to be intense. So they're all 10 weeks, except for the one on the 7th, 8th of July. It's the same 30 hours compressed into 1 week. They're all about $1,000, in case you want to know. So that's basically it. Hope you got something out of it. Thanks for your attention.